Okay, for this lesson on telescoping series, and we're going to talk about why that's even called telescoping in just a moment. First, we have to talk about partial fractions. Now, partial fractions actually is going to work backwards as opposed to what you're so accustomed to seeing. Like, for example, I could give you 1/2 plus 1/3. That's what you undoubtedly saw in early elementary school, and you'd work out that you'd get 5/6. We're so used to starting with two fractions added together and winding up with one singular sum. What we're doing today is we're going to work backwards. We're going to say, what if I gave you something like 5/6? Could we find two fractions that might add or subtract together to get that sum? Now that might sound a little strange at first. You might be thinking, why on earth would that ever even be useful or helpful? I hope you'll see why in a moment. But to jump in here, take a look at this algebraic fraction. 1 over k plus 2 times k plus 3. This methodology is going to say, look, I don't have specific knowledge as what my denominator is exactly. It's all, abstract. But would you agree there is a factor of k plus 2 and also a factor of k plus 3 there? So what I'm going to do is say this is a over k plus 2 plus b over k plus 3. In other words, I'm going to do this decomposition, so to speak. I'm going to try to work backwards. And, at first glance, you look at this and you think, well, where on earth will you go next? Well, I hope you're going to notice that there is a least common denominator in this equation that I just came up with. Would you agree that that LCD would be k plus 2 and also k plus 3? Usually kids would say, well, certainly, those are the only denominators present. Well, a wonderful use of algebra to make an equation like this much nicer is to multiply everything by the LCD. So I'm going to multiply by the LCD. And what's going to happen? Well, here you've got 1 over k plus 2 times k plus 3. And you'd get k plus 2, k plus 3 multiplied over here. Here you have a over k plus 2. Here you'd multiply by k plus 2, k plus 3. By the way, you're going to get so good at this you won't have to show all these steps. I think quite a few of you right now are probably thinking, wow, this is kind of silly. I see what's going to happen. What do we get on the left side clearly? 1. Look, on the right side, the k plus 2's are going to cancel, and you're going to have a times k plus 3. And over here, the k plus 3's are going to cancel, and you'll have b k plus 2. Now, I guess what I want to do right now is maybe move this over just a little bit and get us a little bit of space. See, right now this maybe doesn't look quite as helpful. I'd ultimately like to know what my a and my b are. A and b are specific numbers, and if I can figure out what they are, I can break that original fraction into two separate fractions added together. So I'll tell you what, this is a wonderful way that you can solve, and it's really choosing clever values of k. Choosing smart, clever values of k. I could say, look, this equation, I've got an a, I've got a b, I have a k here, but how about I let k equal what would be a real smart value to plug in? -3. I like that. -3 is fantastic. I'll tell you why. -3 plus 3 is 0. 0 times a, that disappears, doesn't it? What's left? You'd say, well, on the left side, you just have a 1. Hey, look up here. If you plugged in -3, -3 plus 2 is -1. Would you agree you just have b times -1 or -1b? Usually kids would say, well, sure. Tell me what b is. -1. Sometimes kids look at that and they'll say, well, okay, so. Well, guess what? I can also choose another friendly value of k. What else? -2. Now, if you plug -2 in, of course, your left side is still just a 1. But now, this first parenthesis multiplied to a, if k is -2, -2 plus 3 is 1. I'll just have an a itself. And -2 plus 2 would cancel out that expression with the b, wouldn't it? -2 plus 2 is 0, and 0 times b goes away. So all of a sudden, guys, I know what a is, and I know what b is. In other words, this partial fraction is equal to your a, which is 1 over k plus 2. Your b value is -1. And hey, would you look at that? All of a sudden, you have a partial fraction decomposition. So that's what you want to do when you see rational functions inside of sigma. Let's revisit this problem right now. For example 1, you might look at this and say, now wait a minute, I don't recognize this pattern as being geometric. And I certainly don't think it's arithmetic either. After a while, you could look at term by term by term, and you might, try to see what kind of a pattern is. It's neither of those. But look, if you can do a partial fraction decomposition, you're going to say that this whole fraction is really 1 over k plus 2. Now, I'm saying plus -1. How about I just say minus a 1 over k plus 3? And sometimes kids look at that and they'll say, okay, how is that really supposed to help us out? You took the inside of sigma, you took one fraction, and now you've turned it into 2. If anything, dare I say, it might look more complicated. It might look like we made the problem worse. However, let's go ahead and start to break it down. Plug in a 1. What's your first term going to be? What's your first denominator? Well, 1 plus 2 is a 3. Plug in a 1. What's your second fraction? That becomes 1/4. Hey, plug in a 2. What do you get? 2 plus 2 is a 4, and 2 plus 3 is a 5. Hey, plug in a 3. What do you get? 3 plus 2 is 5. Minus 3 plus 3 is 6. Hey, plug in a 4. You get the idea. And again, sometimes kids look at this and it's almost as if they're thinking, so what? What's so special here? Look at the big picture. Look at everything. Not just one parenthesis at a time. What's going to happen? The minus 1/4 and the positive 1/4 are going to cancel. The minus 1/5 and the positive 1/5 are going to cancel. Same thing with this minus 1/6 and the positive 1/6, and this is going to go on and on and on. Now, of course, what can trouble kids, and I should talk to you about this, is you could say, what if you stopped at, say, some nth term? Let's just say that, you're going to have your 1 over n plus 2 minus 1 over n plus 3, and let's just say that we stop there just so that we could, definitely say that we're stopping somewhere. I hope you've noticed every time I stop, it was the first term inside of the parentheses that really would be canceled out. So all of a sudden, someone could say, so your nth sum, it looks like you've got 1/3, and then you've got 1 over n plus 3 here. So if you'd ever come to a stopping point at the nth value, that's what you'd get. But we're going forever. We're going forever. So n's going to get unbelievably large to the point where like a quadrillion would be minuscule and tiny. Now imagine that this denominator is getting super, super big, as large as it could ever become. Tell me about that fraction. It pretty much is going where? Towards 0. So do you know where this is really going, guys? It's really going to 1/3. Because as n gets super big, that 1 over n plus 3 goes away. So as we go on forever and ever, yeah, you're going to get canceling. You're left with that 1/3. This is called a telescoping series. And I think that might sound so strange to us, especially in 2016. Kids might think, who in their right mind would ever name that telescoping? That's so strange. Well, I'm sure you guys have seen pirate movies before, right? Like Pirates of the Caribbean or whatever. Have you ever seen the captain take out his spy scope? His little eyepiece, his little telescope, so he could look further out? And have you ever seen what happens when they push together? It all collapses, doesn't it? So here you've got this really long expansion that pushes together and it all cancels out. That's why we call it a telescoping series. Okay? All right. Well, let's see where we're going next. So we converge to 1/3. Sometimes kids look here and they'll say, well, my gosh, I would guess that we're going to need a partial fraction decomposition. And you know what? We do. We do. So, look, multiplying through by the LCD, help me out. What's your left side going to equal? 1. What would happen if I was multiplying every term by n times n plus 1 here? What's going to be left with our a? A is going to get multiplied to n plus 1. And over here we'll have b times n. Let's choose smart. What's a nice value of n I can plug in? -1, I agree. When you do that, you'd have 1 equals, well, your a term completely vanishes. You'll have -1b, or another way of saying that, b is equal to -1. What's another nice value of n to plug in? I heard somebody say it. 0, you know it. Wow, you plug in 0, 0 times b, that goes away. All of a sudden, you'd have 1a. So a is equal to 1. Do you know what you just found, guys? Is this series, it's a over n. It's 1 over n. Your b is -1, so you'd say -1 over n plus 1. So your a was 1, your b is -1. You just move the negative out in front as a minus. And you're going from n equals 1 to infinity. You can see how quickly you can see what's happening. Let's see. Start plugging in terms. What do we get? Plug in a 1, you get 1 over 1 is 1. 1 plus 1 is 2, so we get 1/2. Plug in 2, you'd say here's 1/2 minus, well, then you get 1/3. Plug in a 3. Hey, I think you see where we're going. Guess where we're going to converge to? 1. Look at all that canceling. What are you left with? Very simple, a 1. Let's take a look at our last one. Sometimes kids look at number 3 and they're saying, you're telling me this is telescoping? You got to be kidding me. It doesn't go off towards infinity. No, it doesn't. But one of the most famous properties of logs is the division property. This is log of n minus the log of n plus 1. Oh my goodness, look at that. Partial fractions can have this form. Let's start working it out. This becomes the log of 1 minus the log of 2. Plug in a 2, you get log of 2 minus the log of 3. Hey, let's plug in a 3, log of 3 minus log of 4. Hey, do you think we need to go and write every one of these terms out? Nope. Certainly not, thank goodness. But what do you think is going to get canceled here? Let's do some thinking. Well, the log of 2, the log of 3, the log of 4. Last parenthesis, what's going to get canceled? Log of 10. Oh, would you look at that? What's left? Log of 1 minus the log of 11. What's the log of 1? 0. Final answer.